All right, guys, let's let me turn this fan off here. Let's get started with the second chapter, the biological perspective. This chapter it's not my favorite, so I'm kind of glad we're getting it out of the way here early on. But yeah, this is a much shorter chapter than the last one, so I want to just kind of get this over with and kind of breeze through it. So I'm not going to take a whole lot of time explaining a lot. I'm not really what you'd call a physiological psychologist or a neuroscientist or anything like that. So a lot of this is not really in my wheelhouse. It's not really my specialty. So let's just kind of get through this as painlessly as possible and see if we can move on. Because again, this is just not. I just can't make it interesting. But it's something that's required that we have to talk about. So let's go ahead and get that done. All right. So the nervous system. The nervous system is the body's electrochemical communication circuitry, made up of billions of interconnected cells. The human nervous system is likely the most intricately organized aggregate of matter in the universe. A single cubic centimeter of the human brain, about the size of a sugar cube, contains well over 50 million nerve cells, each of which communicates with many other nerve cells in something called information processing networks. Now, what makes the brain truly remarkable is that although it's so very densely packed with neurons and nerve cells to begin with, each one of those nerve cells is intricately connected to thousands and sometimes even millions of other nerve cells. And the whole thing is just kind of like this whole integrated network of connections and pathways that have been forged and kind of highlighted with every single experience you've ever had. Again, I think we talked about it in the last semester or the last chapter, how a memory, we think, is an actual path that has been traced and forged by very specific neurons in a very specific order, in a very specific way. And each time those neurons light up, each time they are activated and they follow that prescribed path through the neural network, then that memory gets sparked. So it's literally physical connections within the brain. And every time that you learn something new and every time that you appreciate something or experience something, your brain actually physically changes. Every time you read something or commit something to memory, you are actually forging new connections with the actual neurons in your brain. They are physically changing. So your brain is a constantly updating and constantly evolving, pretty much computer. The computer brain simile is very actually quite accurate. It tends to process information kind of serially, like there's a set specific order for how things are stored and how things are recalled. You have a working memory, which is kind of like the RAM in a computer, and you have long-term memory, which is kind of like the hard drive storage. So the computer to brain synonym is actually a pretty good one. Several extraordinary characteristics allow the nervous system to direct our behavior. These are complexity, integration, adaptability, and electrochemical transmission. So we're about to talk about each of those here in turn. The first is complexity. The brain and nervous system are enormously complex. The brain itself is comprised of billions of nerve cells. That's billion with a B. That is a lot of activity and a lot of matter just kind of scrunched up together. The orchestration of all of these cells is a truly awe-inspiring task. How all of these things are able to communicate with each other and how they're able to form new memories and new sensations and things like that is truly remarkable. We don't know of anything else in the known universe that works nearly as symphonically or as together, yes, so choreographed that everything just seems to kind of work itself out, and it has ways of protecting itself, protecting you from trauma and things like that we haven't even begun to understand yet. We've only really kind of scratched the surface of what all the brain really has to offer. And you've heard the saying that you only use about 10% of your brain. Well, that's true. You only have access to about 8 to 10% of the working capacity and the capabilities that your brain is actually able to do. If we were able to somehow take a pill or unlock the other 90%, the sky is really the limit. We don't really know exactly what that would even look like. There's a really good movie with Scarlett Johansson. I think it's called Lucy or something like that, where they developed this kind of synthetic street drug that allows you to awaken and access your entire brain, and things, not surprisingly, go wrong very, very quickly. So check that out. It's got Morgan Freeman in it too, I believe. So go check that out if this is really kind of interesting to you. Integration. The brain does a wonderful job of pulling information together. Sight, sounds, touch, taste, smells, hearing, genes, environment, etc. The brain integrates all of these as we function in our world. Again, we are bombarded by billions of pieces of information every second. Our environment is constantly just lambasting us with stimuli and all that sort of mumbo noises and lights and sounds and things that we have to pay attention to. And again, we're only able to focus on a very, very small portion of that. And the brain is able to kind of take these shortcuts and kind of cut down its processing power, if you will, and process things in the environment kind of automatically. And we'll get more into this really in the next chapter, how things happen in your environment and you're not even aware of them, but you're still kind of subconsciously processing them. Subliminal perceptions, things like that. We'll probably start on that on Wednesday. But your brain is attenuating to every single thing that's in your environment, but you're only consciously aware of a very small fraction of what is going on. The brain and nervous system have different levels and many different parts. Brain activity is integrated across these levels through countless interconnections of brain cells and extensive pathways that link different parts of the brain. Each nerve cell communicates on average with 10,000 others, making up literally miles and miles of connections. So if you take each of these billions of brain cells and you kind of exponentially connect them with each one of those with up to 10,000 others, we're talking about, trillions and quadrillions of connections in your brain. And if each connection is a memory or a sensation or a piece of knowledge or anything like that, you can see quickly how this can get exponentially bigger. And the more we are able to access, the more we learn about this, the more rich and diverse this whole phenomenon that we have becomes. And the brain, again, is a very, very complex, very, very humbling and stunningly integrated and just enormously complex. We have very, very little knowledge of what the brain is capable of. The third part, adaptability. Our brain and nervous system together serve as our agent in adapting to the world. Although nerve cells reside in certain brain regions, they are not fixed and immutable structures. They are constantly adapting to changes in the body and the environment. This is called plasticity. This is what I was just talking about, how things, your brain is constantly changing, your brain is constantly forming new connections and dissolving old ones. Electrochemical transmission is the fourth and final part. The brain and nervous system function essentially as an information processing system, powered by electrical impulses and chemical messengers. Epileptic seizures are the result of abnormal electrical discharges in the brain, much like electrical surges during thunderstorms. So people with epilepsy, the reason that they have the seizures that they do is because their brain is essentially overactive, and it completely fires the entire neural network, and the person convulses like if you were to grab hold of an electric fence. So yes, your brain, the way that the brain communicates, not only with itself but also with the rest of the body, we'll get into here in just a second. But the electrochemical transmissions, the way that the brain can send messages down the pathway to your arms and to your legs and to your stomach and to your eyelids and everything else is another yet truly awe-inspiring task at how efficient it is and how powerfully fast these signals and these messengers are able to travel. Pathways in the nervous system. As we integrate with and adapt to the world, the brain and nervous system receive and transmit sensory input. They integrate the information received from the environment, and they direct the body's motor activities. Information flows into the brain through the sensory input. It becomes integrated within the brain and then moves out of the brain to be connected with motor output. So your brain basically not only receives sensory input from your fingers and your toes and your body and your legs and everything else, it also processes that information, and then it's going to send a motor command or a motor order back out down the same pathway to the hand or the foot or whatever. The nervous system possesses specialized pathways that are adapted for different functions. There are basically two types of nerves. The afferent nerves or sensory nerves carry information from the body to the brain. So if you were to put your hand on like a hot burner or something, the afferent nerves would be the sensory nerves in your fingertips that would sense that yes, this is hot, this is not good, and it would send a message up the nerves in your arms, into your chest, up through your neck and into your brain. Your brain would process that, and then it would send the motor command through your efferent nerves. These are your motor nerves, and they're going to carry the brain's output. So the efferent nerves come from the brain back down to the body. So your afferent nerves would be the nerves in your fingertips and things like that, the sensory nerves that are going to send the signal up to your brain that, hey, this is hot. And then the brain will process that and say hot is bad, and, need to move your hand. And then it's going to send that command back down the efferent nerves to the arm and allow you to lift up your hand. This is done through things that are called neural networks. And again, you have a neural network for every single possible function in your body. People who are paralyzed have lost the ability to make that transmission, have lost something along the neural network, is not able to be processed. It's usually a spinal injury or something like that. But the neural network, the connection between, the fingertips or the foot or the leg or whatever, back to the brain, and the motor command back down, something along that chain has been disrupted. Divisions of the nervous system. There are two primary divisions of the human nervous system. The first is the central nervous system, or CNS, and this consists of the brain and spinal cord. This encompasses more than 99.9999999% of all nerve cells in the body. And then you have the peripheral nerve system, which is the network of nerves that connects the brain and spinal cord to other parts of your body. So you have the brain and you have the spinal cord comprising the central nervous system. And if it is not brain or spinal cord, it is the peripheral nervous system. That is every other nerve in your body. The peripheral nervous system has two major divisions, the somatic nervous system and the autonomic nervous system. The autonomic nervous system consists of sensory nerves whose function is to convey information from the skin and muscles to the CNS, and motor nerves whose function is to tell muscles what to do. So the somatic nervous system actually contains both the afferent and the efferent nerves. These are the body nerves, the body's communication circuitry. And then you have the autonomic nervous system. This is the division of the peripheral nervous system that communicates with the body's internal organs and monitors processes such as breathing, heart rate, and digestion. So you have your somatic nervous system, you have your autonomic nervous system. The somatic nervous system is usually things that are under your control. The autonomic nervous system is all of the things that are processed automatically. So automatic, autonomic, you can use that as kind of a neat little mnemonic to help yourself remember that. These are things like, your stomach digesting your food, or blinking or breathing, or your hair and fingernails growing, or things like that. Things that you don't have to have actual conscious control over, that just kind of process and happen automatically or naturally. The autonomic nervous system is further divided into two parts. One is the sympathetic, and the other is the parasympathetic. The sympathetic nervous system is the division of the autonomic nervous system that arouses the body. This is the part that gets you excited. This is your fight or flight response. The parasympathetic nervous system is the division of the autonomic nervous system that calms the body. So it's almost kind of like a binary system. It's either on or it's off. The sympathetic nervous system is, again, that part that is responsible for increasing your breathing and keeping things going that should be going. And the parasympathetic nervous system is that part of you that kind of calms things down or shuts things off once they are no longer necessary. All right, neurons. Within each division of the nervous system, nerve cells, chemicals, and electrical impulses work together to transmit information at speeds of up to 330 miles per hour. And over the short distances that most nerve signals have to travel, that is blindingly fast. Information can travel from your brain to your hands or your legs or your lungs or your heart in a matter of milliseconds. And again, the heart beating is another part of that autonomic nervous system that you don't really have conscious control over. You can't, some people can train themselves to learn to control their heartbeat, but you don't have to. It happens in the background. You don't have to actually tell your heart each specific time to beat. It's like you don't have to tell your lungs to breathe or your eyes to blink or anything like that. It all happens kind of in the background. There are two types of cells in the nervous system. Neurons and glial cells. Neurons are nerve cells that are specialized for processing information. They are the basic units of the nervous system. The neurons are the workhorses. They're the ones that are responsible for passing information, kind of like a relay race from one nerve to the next. And glial cells are cells that provide support and nutritional benefits to the nervous system. These are kind of the support, administrative assistants of the neurons, if you will, those that keep the neurons healthy and running at peak performance. Most neurons are created very early in life, but their shape, size, and connections can change throughout the lifespan. Again, you're constantly changing, you're constantly evolving. You're forming new connections millions of times a day. Every neuron has a cell body, dendrites, and an axon. So 3 parts basically to every nerve cell, every neuron. The cell body contains the nucleus, which directs the manufacture of substances that the neuron needs for growth and maintenance. Dendrites receive information and orient it towards the cell body, and the axon carries information away from the nucleus and pushes it towards other cells. So you have the cell body, which is pretty much the nucleus of the cell. You know what a nucleus is. It's the brains, the workhorse, the part that processes everything. You have kind of long, dangly bits at the end of the cell body. These are called dendrites. Dendrites are responsible for pulling information from the previous nerve cell in the chain and pushing it towards the cell body. And then the cell body processes that information, that signal, and makes a decision or a determination whether this signal should be passed on to the next nerve cell or whether it should pretty much die there. If it makes the decision to push it on to the next nerve cell, it pushes that information from itself to the axon, to its own axon, which again fires that information all the way to the very next cell. So information flows inside of a neuron one direction. It enters with the dendrites. Dendrites push it to the cell body. Cell body processes that information, and then it pushes that information along its own axon to the dendrites of the next, and the chain continues, etc., etc., etc. A myelin sheath is a layer of fat cells that encases and insulates most axons. By insulating axons, myelin sheaths speed up transmission of nerve impulses. So you can think of it as kind of like the coating on the outside of a speaker wire or something. It essentially minimizes signal loss. It kind of helps insulate the axon and allows it to basically conduct electricity much better. Axons without myelin sheaths are not very good conductors of electricity. With the insulation of myelin sheaths, axons transmit electrical impulses and convey information much more rapidly than they would if they had not. So the myelin sheath basically just makes the axon much more efficient, and it makes it much easier for it to push that information, that signal, down the length of itself, and be able to process that information and push it onto the next cell itself. To transmit information to other neurons, a neuron sends brief electrical impulses. These are called clicks through its axon to the very next neuron. And by changing the timing and rate of each signal, the neuron can vary its message. So neurons can have the ability to kind of increase the urgency and flag it as very, very important. This is a high value message, and it will push those messages much, much faster than it would something that is not nearly as serious. So, putting your hand on a burner, that would be a very, very fast moving signal because that is very, very urgent. It can, cause a lot of damage. So your brain really processes that very, very quickly and sends the corresponding efferent message down at its maximum capacity. That is red flagged, that is highlighted as ultra important, and everything else just kind of ceases. So things like when you sneeze, or when you are in pain or something like that, you'll notice that kind of every other sense of anything kind of gets narrowly warped down, and really the entire source of your focus is on that high moving, possibly very, very dangerous signal, because your brain essentially kind of shuts itself off from conscious control and prioritizes those things that might potentially be life-threatening. Axons fire on an all or none principle. Once the electrical impulse reaches a certain level of intensity, called its threshold, it fires and moves all the way down the axon without losing one single shred of its intensity. So once the cell body of that neuron decides to send the message on to the next, it stimulates the axon. The axon carries that information, and it carries it all the way. It doesn't do it halfway. Once the cell body decides to fire that axon, it goes all the way down pretty much instantaneously. So what happens when a neural impulse reaches the end of an axon? Nerve cells don't actually touch each other. It's not like the axon of the sending nerve kind of wraps itself physically around the dendrites of the receiving nerve. There's actually a small little gap. So the axon ends, and then very, very short distance there's this small kind of gap, and that gap is called a synapse. And we're going to talk about neurotransmitters here in just a second, but the neurotransmitters are the things that are responsible for pulling the information, actually converting the information of the sending axon. It converts it from electrical to chemical, and then it kind of ferries that signal across the synapse and decodes it and plops it right down on top of the dendrites of the receiving axon, and the next nerve in the chain, and it converts the electrical signal that it carried across the synapse back into an electrical signal, and the dendrite accepts that electrical signal and moves that signal up to its own cell body, where it's then processed and sent on the axon. The signal crosses that synapse, picked up by the next neuron's dendrites, and so on and so forth. So you can think of this as kind of a relay processing, where if you're in a relay race, you carry your baton until it's time to hand it off to the next person. And once you hand that off to the next person, you're done, and it's his job to carry the baton onward. Synapses are tiny junctions between neurons. The gap between neurons is referred to as a synaptic gap. We just talked about that. Most synapses lie between the axon of one neuron and the dendrites or cell body of another. Before an impulse can cross the synaptic gap, it must be converted to a chemical signal. Again, the neurotransmitters are those things that are responsible for converting the electrical signal that the axon carried and converting that electrical signal into a chemical signal. And again, the neuron kind of floats across the synapse to the dendrites of the next receiving neuron, converts it from its own chemical signal back into an electrical signal that the neuron can understand, and the dendrites receive that electrical signal and push it on to the cell body, and so forth and so forth. These neurotransmitters, quote, transmit the signal being relayed from one neuron to the next across the synaptic gap. And then we kind of get into the different neurotransmitters. You know what? Don't worry about the neurotransmitters. I'm not going to ask you about any of those on the test, even though they're in red. Don't worry about acetylcholine and GABA and norepinephrine and those types of things. I think that's a little bit probably beyond the scope of this class. You'll if you decide to take a little more psychology, you'll definitely take a physiological psychology class and probably a neuroscience class, and you'll get all into this, all the different chemicals and mapping out the regions and structure of the brain. But I really think that's probably a little bit beyond the scope of what this class is. This is not a biology class, but kind of an introduction to biology and the nervous system and things like that, I think is probably important for you to, especially we're going to kind of piggyback on this in the next chapter, Sensation and Perception, about how we take in signals and cues from our environment and how we process those in the brain and things like that. So I think you'll really enjoy this the third semester, or third chapter. God. But that is it for biology. I told you it was going to be short and sweet. Again, make sure that you watch these videos and follow along in your notes. I'm reading the notes word for word. I'm looking at them on my iPad right now as we speak. So that's really the source of where a lot of your information and a lot of your test questions and things are going to come from. So again, make sure that you follow in your notes. I will post these notes and this video as soon as I'm done here. All right. So as always, if you have any questions, send me an email, send me a message. I believe class is still set to start on Wednesday. I'm recording this on Monday, so day after tomorrow I will see you guys bright and early. I guess until then, I will see you later. All right, take care.